This is our last week of lectures, and we're going to finish off talking about pH. pH has a lowercase p, strangely enough, and an uppercase h. No matter if it starts a sentence, we still use a small p. And we'll go ahead and we'll define pH here in a minute. It's a measure of acidity. So whenever we're trying to measure how acidic or basic a solution is, we can talk about a pH number. Now, if you recall earlier, we talked about water actually self-ionizes, and so we wrote down a reaction that looks something like this. So H2O actually breaks apart into H plus and OH minus ions, and in pure water, it turns out that these have a concentration of exactly 1 times 10 to the minus 7 moles per liter, and that's for pure water right around room temperature. But it turns out that when you add solutions of acids or bases to water, it will disturb the balances of these two concentrations here. But it turns out that the concentration of H plus times by OH minus is always equal to the same value, and at room temperature, it's equal to 1.0 times 10 to the minus 14. And if anything makes 1 go up, like the H plus goes up, then the OH minus has to go down so that it stays equal to this constant. This constant here we actually call K for constant. Technically it's an equilibrium constant, and we write a little W there because that's the equilibrium constant for water. So we can see that in pure water, if this is 10 to the minus 7 and this is 10 to the minus 7, they multiply to give 10 to the minus 14. But if we do anything that raises the concentration of one, it will act to lower the concentration of the other. And in many ways, I think of this as sort of a seesaw. So you've got the H plus concentration on one side and the OH minus on the other, and if you add an acid, it will raise the one concentration, but it will lower the other, but they still multiply together to give that same constant, 1.0 times 10 to the minus 14. We can examine some blood and calculate the OH minus, the hydroxide ions concentration. If, say, the H plus concentration in blood is 4.3 times 10 to the minus 8 moles per liter, then we can use this information to find the hydroxide concentration. And we really just go back to this equation. The concentration of H plus times OH minus is always a constant, 1.0 times 10 to the minus 14. And so if we know this and we know this, and we don't know this, we can rearrange to find this. If we divide both sides by the concentration of H plus, then that will cause the H plus concentration to cancel out on this side, and then we'll be just left with the OH minus concentration all by its lonesome self. So we can go ahead and we can plug in, and so we have 1.0 times 10 to the minus 14 divided by 4.3 times 10 to the minus 8. And if we go ahead and we do that division to two significant figures, we get 2.3 times 10 to the minus 7. And if you noticed in this section here, we've actually been a little bit naughty. We've left off our units here, so you might expect if that's a concentration and that's a concentration, that to be units of molarity squared. But what we normally do is we conventionally leave off the units and we just sort of plunk them back at the end. There's another reason for why we do this actually, but trust me, you really don't want to know the other reason unless you're a chem major, and even then maybe you don't want to know. So we're just going to put them back on at the end. So units of concentration are moles per liter or molarity. Now, if you have a scientific calculator like a TI-30 XIIS, you might be wondering, how do you type these in on your calculator without going crazy? And the answer is you actually use a button on here called the EE button. And the EE button, let me go to a pointer. It looks something like that. You have to hit the second function button and then this button here, and it generates EE. And what EE does is it takes the place of times 10 to the minus 14. So if you are trying to type 1 times 10 to the minus 14, what you do is you type 1.0. So on your calculator, you hit 1 and then point and then 0, and then the times 10 to the power, you would hit second function EE. So on your calculator, right, you would hit that second function EE, and then you would hit minus 14. So we're going to use this minus here, and then the 1 and the 4. So you should make sure that you are aware of how to enter this on your calculator. And again, 4.3 times 10 to the minus 8, you would hit 4.3 EE, and then minus 8, and that would give you 4.3 times 10 to the minus 8. And that is the easiest way by far to enter scientific notation on your calculator. You might say, well, I don't really want to do that, right? Why not just write times 10, and then the power button on here looks like this little caret symbol here. And you can do it that way if you want to, but if you do it that way, you might want to use parentheses around the top and the bottom. So if you want to do it the old-fashioned way, you can do it just fine. You just have to use parentheses around the top and the bottom. Otherwise, when you do the division, sometimes it'll only divide by the 4.3 instead of the 4.3 times 10 to the minus 8. So you'll actually be off by 16 orders of magnitude if you don't put parentheses around the top and the bottom here. You might also be interested, is this acidic or is it basic? And so if it's acidic, the H plus concentration is actually bigger than the OH minus concentration. If it's basic, the OH minus concentration is bigger than the H plus. And so the OH minus concentration is 2.3 times 10 to the minus 7, and the H plus is 4.3 times 10 to the minus 8. So 10 to the minus 8 is smaller than 10 to the minus 7 by a factor of 10. And this number here, I believe, is about 5 times bigger than this number here. So it is definitely a basic solution, and most blood tends to be basic. And the fundamental definition of basic versus acidic is it is basic if the OH minus concentration is the bigger of the two concentrations. So this is basic. It'd be very nice if we had a nice easy way to determine if something were acidic and basic rather than having to do this comparison. And we do actually, and this leads us to the concept of pH.